What's up, guys? It's your boy Lorenzo, and welcome back to Physics 2 Lab number 3. So we're working with the magnetic field of a bar magnet. Okay. The purpose of this lab was to discern the distance dependence on the magnetic field due to the small bar magnet. In theme with the other labs, we have a computational model and experimental model. Experimental model is one we perform math on in the real world, and then we go flow script, do a computational model. You'll see both of these in this lab. Big focus here. You see our results that I got. We'll go over that. Big focus here is the Biot-Savart law, where the linear and use of the linear data analysis that I'll show the results of soon. But we got our assumptions here. The magnetics. Here we go. Let's make this a slideshow. We got the magnetic field is assumed to be a dipole from the magnet. No air resistance, Newtonian model. We are expecting an inverse relationship between the net magnetic field and the distance of our readings or observed point. So our initial condition was the bar magnet and the magnetometer. We got our system surroundings being the bar magnet, everything else. And first things first, you had to calibrate the magnetometer and basically see where you were working on it in a Cartesian plane, X and Y direction, parallel and perpendicular. So here's what we observed from just playing with the magnetic reader. Okay, so when you're far enough away, it's 0, that's showing that the magnetic field decays. And when you draw in closer to the bar magnet, of course, your magnetic reading is increasing. And what we can assume here is that there is an inverse relationship between the distance and the strength of the magnetic field. We also had to avoid interference from the Earth's magnetic field, and we were able to attenuate that concern by correctly positioning the magnetometer. We've got some calculations here. Of course, we plotted 3 points. We've got this linear curve here, the slope of which is measured here, and then we did some math to find k based on this -12 value. And then we apply that to the formula for u. And so this is all derived from the Biot-Savart law. Now next, we've got the conclusions. Just like I said before, we determined there's an inverse relationship between the net magnetic field and distance. Got our u, got our n, which were important for the results from our calculations, also the results from our linearization. And then we've got human errors, of course, misreading the distance on the ruler, and then environmental conditions, external error, which is Earth magnetic field, and possible interactions from devices. Here's our questions. Basically, what if you hadn't oriented your experiment to compensate for magnetic north? Well, it's possible that Earth's magnetic field would cause superposition at the observed points and skewed the results, basically constructed or destructed with the magnetic field. And what if you were to stick 2 identical magnets together at the end? Of course, if you had 2 magnets, you have double the charge, but if they're end to end, the only thing that would change is the strength of the field. None of the directions would change. But let's dial back a second. We want to look at this flow script code. Okay, and so here we are. We've got our u 0 over 4 pi. We've got our magnet. Okay, you've got your initial conditions. We're creating the vectors here. And essentially what you've got is a visualization of the magnetic field. We're going to run it and show you guys in a second. And there it is. Oh, there we go. There's our magnet. There's magnetic field visualization. Of course, you got the dipole going. So you've got the dipole moment, and you've got the perpendicular and parallel readings. All right, that is it for this lab. And there we go.